So welcome, Vaughan Vernon. I wish you a pleasant experience.
Okay, well, thank you for inviting me to do this. This is
3, 2, 1, go.
Thank you for inviting me to present, and it's an interesting situation that we're in now, but we're making the best of it. If this becomes more normal over the years, then probably what we'll have to do is improve the technologies that we're using to do this, but for now, it's the best we can do. We're agile, right? So I wanted to talk about sort of a soft tech kind of topic right now. This is get these three things right or else. And this has to do a lot with, you know, what is our idea about transformation, let's say. Is transformation only digital, or are there other transformations that we need to make? So as just a little bit of an introduction, I had that in mind. Okay, so you probably know me for this, but I also am known for this now. This is my open source reactive platform, and several people are contributing to it, and we are actually paying developers to work on this, and it's been a lot of fun. So I'll be introducing this a little more in my next talk. So modernization. What is modernization? Everybody's shooting for modernization, aren't they? If all you have right now is a web app from 20 years ago, not good enough. It's not modern. Transformation. Do we do things digitally, or are we missing the boat with digital? So do we need to transform to digital transformation? So my question, though, is more about transforming this situation, the big ball of mud. Frankly, wherever I go, all of the clients that I engage with currently and probably for the past 4 to 5 years, it's all about this problem, the big ball of mud. Everybody's in this situation. It is damaging business because you can't innovate in this kind of software environment, and you can't innovate because you can't make changes and releases in a timely manner, not according to today's expectations. So some teams are talking about releasing multiple times per day, maybe even 5 to 7 or even more times per day. But you're not going to do that with this kind of software. Companies are doing well. The system, they tend to be highly coupled and highly dependent, but not well organized. And the conversations that you have around this software focus in one area, but by changing something in one area, you can easily break things in another area. The only thing wrong with this illustration or this diagram here is that there aren't enough boxes and we're not really showing the lines of dependency. So what do we do about this? Well, we can't just throw it away. This is legacy. It makes money. And the reason that, uh, the very reason that it makes money is the reason why we can't just get rid of it or easily replace it or start tearing it apart and putting it back together, because it would stop making money during that time, and even highly potentially not make money ever again because of the damage we could do to the system. Pardon me, my sniffles do not indicate coronavirus, fortunately, right at this time. I think it's just maybe some allergies in our springtime here. I apologize for that. So we get a lot of times to this situation of the big ball of mud because of this anti-pattern. Actually, some people think of this as a valid pattern, but I actually do not consider an anemic approach to software development as a domain model. So the official name of this anti-pattern, or what I call an anti-pattern, is anemic domain model. But I'm going to insist that this is nothing like a domain model at all. Um, including the name domain model is too highly complementary to this kind of model, and I'll explain why. Notice the annotations that are very typical. Now, this is from a Java perspective, but this can happen in really any language where we have this class. In this case, we're talking about a client, and this client has some string fields in it. Notice that each field has an association to the database, and so does the whole class. The class itself is known as an @entity, and maybe when we see @entity, we're being a little bit encouraged by this, because we're saying, oh, let's see what this entity, maybe it's a real domain model entity. Let's see what it has to offer. And then we look immediately inside, and the first thing we see is @ID, and then a bunch of @columns. Well, maybe not so bad, because let's go see what the behavior is. Okay. And what do we find? We find something like this. Actually, there is no behavior. The behavior is just setting data inside the client, and then this client object gets mapped into the database. So what does this mean? Why are we making these changes? When you look at this client and the operations being done here, set address 1, set address 2, set city, so forth, what's the impression that you get? Oh, well, we're creating a postal address on the client. That's obvious, isn't it? But is it really? Is that what we're doing? Is it a creation, or is it an update? And if it's an update, what kind of an update is it? Are we correcting some sort of spelling error in the street address? Or which street address? Or has this client relocated? And if they relocated, might that be interesting to another part of our large system that is operating on this information? So think about the overall impact of this, and think about how many places where these setter methods could be used together or independently, depending on the use case that's being performed. And without, it could require you to actually go into the user interface and trace down the path of the use case until you reach this point to understand why this is being done. And actually, you can't go to the UI and figure this out. You have to kind of trace backwards, right? You have to say, oh, I'm in this method that's now setting these address fields, and I need to go back one level and see what called this, and then I have to go back another level and see what called that. And oh, now we're in the UI. Where did that request come from, right? And what are we gaining from all of this? Well, not much, actually. So when I'm talking about transformation, there are really two kinds of transformation that is essential today. Um, there is definitely a need for digital transformation. We must make our software more, uh, you know, more powerful in terms of the business actions, the business features or capabilities that it implements. And certainly, we can replace a lot of manual labor still, even in today, even since, computers have been a big deal and software a big deal for, 35 to 40 years now. Still, we haven't made the digital impact that we could. And so we should be transformative in digital transformation. But are we really going to be able to achieve digital transformation if we do not transform our own behavior as software developers? So a lot of teams now think that, pardon me, microservices are the answer, right? So let's just take that big ball of mud or even a greenfield project, and we'll just break everything up into microservices, and that's the answer. Well, it could be, but most experiences that I have is that teams are doing this incorrectly as well in many different ways. And I won't list all of them, but a few obvious ones that maybe you've heard of or even experienced is the microservices share a database, or the microservices share services that do common things, or even libraries that do a lot of common things. And so the libraries between the microservices is really providing, sort of this cheating kind of interface between the services. And there's a lot of secrets going on there that are not explicit. And so what do we end up with? Well, yes, again, a distributed big ball of mud. So are microservices really the answer? I think that transformation is fundamentally needed in software development. And most people who are interested in domain-driven design will hardly agree with this. But this message is not being disseminated broadly enough. And the message really is the transformation in what we build or how we build it? And I think that to be successful with what we build, we must be first successful with how we build it. Because ultimately, any digital transformation that we attempt will be brittle and highly potentially uh, succumb to all the problems that we've experienced over the past 40 years and more. So let's talk for a few minutes about how we build. This is actually a transformation. If you look back to that big ball of mud, the comparison, and to this could actually be the same software that was functioning in that big ball of mud, but what advantages do we have in this situation? Well, If we want to look negatively, we could certainly zero in on the individual objects. Look, there are some really big objects there, right? Might we call them God objects or something like that? They have too much responsibility, too many lines of code, they're confusing. But look at the advantages of this. 7 different organizational structures within this larger structure. Um, and notice there's a coupling between certain parts of this organization, but I think we could refer to this as loose coupling. So objects within each of these uh, medium-sized structures, let's call them modules. Each of these modules has some dependency on another module, but notice that the dependencies are not at the inner object level. Instead, they are at a boundary level. So I can't really point here, or maybe I can with my mouse if you can see this. This is what I'm talking about. The dependencies are at the boundary level between these modules and not from object to object within the modules. What is the difference between this and a microservice or a set of microservices? Let's say that we took all 7 of these medium-sized structures or modules and took them out of here and created 7 microservices. What would be the difference? Actually, most of the difference is only in this connection between the modules. This as maybe an asynchronous yet in virtual machine or Java virtual machine or process, as in a .NET solution, this would be like an asynchronous thread or even a synchronous thread request across these 2 modules. But in microservices, this would be the network. Unless, of course, there was some sort of strange library in between that that didn't actually introduce the network or did or sort of hid the network from us. So there, in terms of transformation, this is a monolith. So we don't have to go to microservices to transform the way that we develop software. You can still transform our mentality of the big ball of mud into this. And notice, because we don't have these object to object dependencies across these modules, we can refactor this oversized, let's say, domain object, or whatever this has in terms of multiple responsibilities. We can break this up into single responsibilities, and from here to here, there's no breakage. Whereas if we were trying to make that kind of change in a big ball of mud, we don't actually know all of the places that are dependent on that. And we will soon learn them. It might take days or weeks, but when the software starts failing somewhere mysteriously, and we finally we trace it back to, oh, there was some change over here that caused a breakage clear over here, and we didn't realize that that was happening. So, transformation. And notice the code transformation. The client that I previously showed you now has explicit behaviors that show the reason for a client address change. Here's one of the reasons: relocate to postal address. So the client is explicitly relocated to a new postal address. Recall also that all of those attributes that we previously had on a client were individual attributes, and it's not uncommon to have 20, 25, 30, or even more individual string and or integer attributes on some sort of entity that they're just being mapped in and out of a database. But notice here that we actually have an explicit postal address concept, and this postal address concept is just that. It describes a postal address, and the postal address describes the location of the client. So these are actually not very complex wins that we can introduce into our software. Notice also that this relocate to, in terms of the lines of code in this client, it's far less lines of code than the code that was using the setter methods before. And the client software of, or the client layer of the domain model, in this case, would have a single method invocation on this client.relocate to. Then notice another advantage that we have is that not only do we set the postal address, but we also emit a new client relocated domain event. Recall before that maybe we're interested in other parts of the system being aware that a client relocated. And we can easily think of a use case for that. This is where a client has already purchased a product online and they didn't realize that they had their own postal address, their old postal address, registered in their client description, until they saw the order placed and it says this order will be shipped to such and such an address. Well, it's too late. They shouldn't cancel the order, but they should be able to easily go to their client profile and show a relocation address. And that change can easily catch up with the order that's going through the order system, through fulfillment, and finally through shipping. And because of that, the downstream that is consuming the order information can be alerted to the client relocation, and those parts of the system can also be updated to reflect the client relocation, just in time or just before. Notice another advantage. We can actually test this client. Notice the test below, client tests, client should relocate. We can perform a relocation with a single line of code using some fixtures. So we would have a client fixture and a postal address fixture to assert that the client was relocated. But now notice that we can check, we can assert against that the postal address in fact was changed, but we can also assert now that a client relocated event was emitted from that client. We can actually have a test that probably is no more than 3 to 5 lines of code and is very reassuring to us that this client relocates. If you were to attempt to test the previous client, you must admit, I hope, that that is really not something that you can test, because what are we testing? We're only testing that that these 5 or 6 setter methods change the state of the internal client. We're not testing that a relocation occurred. This is a very subjective kind of thing to test when we do not have rich behaviors that are intention revealing. This is a transformation that tells us exactly what happened. So another failure that we have in the industry is our communication. This is an illustration of where executives, let's say, in the boardroom or in this kind of situation where the executive leadership meets, they envision this new digital transformation. And in order to make this digital transformation occur, they have to communicate to others. And unfortunately, this communication isn't directly from the executives to the software developers. The software developers are below this funnel um, structure here, or this funnel device. And notice, while there's a broad vision and broad knowledge at the top, where intentions are fairly well understood, but not in great detail, this vision enters into a communication channel. And the broad communication first takes place between this executive or a number of executives and the, the team that works directly under them. How many layers are there between here? Well, what we're going to do is not only say that this is a funnel and that knowledge trickles very, very slowly out of this, but we're also going to insert a filter at every single communication division within the organization. This could be dozens, actually, depending on the size of the organization, or it could be 4 or 5. But you know what? When you play the telephone game, if you're familiar with that game, how many people have to be told from the originator of some message to the next person? When does that message actually, how many ears does that message have to pass through before it's distorted? Literally, with one single person in between the originator and the one following the one who the originator said. So the third person involved will already get an obscured story, an obscured communication. You go another 2 or 3 levels, and that message will be somewhat recognizable according to the original, but the further it goes, the funnier that game becomes. The problem is, this is not a funny game to play. The other thing that happens in this case is that the developers also have the same kinds of layers and the same kind of slow communication back up to the leadership. So the limited and interpreted understanding that they had before is now a misinterpreted vision with a lot of missing knowledge. And by the time that the communication reaches the executives, and possibly with even a demonstration, a software demo of the features, the executives could be shocked by the level of difference between what their communication was and what their vision was and what they actually received. And because of the time lag between both the left and the right side of this diagram, and also the vertical time that occurs on each of these sides, by the time the executive actually sees, or the executives actually see the vision that is transmitted through the delivered software, it can actually be too late to turn back and correct this situation. Also, we have the same kind of tactical failures happening with this team. And even if they do, even if they are instructed to go correct the vision, how does the software now, how is it structured? Will they be able to make those clean refactors or even redesigns within modules? Likely not. Instead, they will be fighting with this sprawl of software across what could be several modules, and yet that isn't there. And so these kinds of situations happen time and again with our software, uh, and the teams and the companies involved, the organizations involved, and it really becomes uh, a strategic failure. So the best situation that we can create is where the broad vision and knowledge is given directly to a software development team. But the communication doesn't stop there. We don't end with command and control where the executive says, or the person who is in charge of delivering this vision ultimately as software. It doesn't end with them giving a command to the 4 developers on the right-hand side, and those developers just taking that command and being controlled by it. They're just somehow going to miraculously deliver great software. The communication has to go beyond just the vision statement itself. The communication has to continue. Um, and it doesn't have to be a full-time communication, but there has to be ongoing communication. So this is where we can unite both strategic and tactical software development, because here's what we actually face. The complexity of the business problem itself is generally very high when we are trying continuous code. This is spaghetti business, okay? Spaghetti business means that the business is really far more complex than the software, than a programming language is to use. We are trying to solve extremely complex business digital transformation problems with a programming language and some technologies that we can actually know pretty well, and yet the business problem is much more complex. So when you get into this kind of situation, in this kind of business situation, business complexity, we don't want to multiply the complexity by adding complexity to the software implementation itself. We want to instead tackle the business complexity with our software, but that means that we're going to have to use our brains to tackle the business problem. And when we tackle the business problem, we can simplify as much as possible the actual software implementation. And simplification doesn't mean easy, but I must say, simplification is far easier to deal with in the long term. So take the big ball of mud, which we've probably all experienced far too much of, or the domain model that I later showed with explicit behavior, and mentally choose which one you would rather work in. I think the answer is clear. We've all heard of Feynman, right? A marvelous um, physicist, and he was known for having, this problem-solving algorithm. So this was this brilliant man's problem-solving algorithm. First, write down the problem. 2, think very hard. 3, write down the answer. Do you know the problem with software development? We skip the first 2 steps all the time. We don't even know how to write down the problem. And when we don't know how to write down the problem, we don't think very hard. And so instead, with software, we just write down the answer. And it's the wrong answer. Even if we can ship the software, the fundamental underlying stability of the answer that we give is wrong. So this is all led up to the 3 things we have to get right or else. And I have to say too that this first thing that I'm going to share with you, Conway's law, is something that technically really you don't get right. It's like saying um, I'm right with gravity. Okay, so what does it mean to be right with gravity? Well, it probably doesn't have much meaning. Well, it could mean we decide not to jump off a 30-meter high wall or roof or something like that on a building. So that could maybe be being right with gravity. So we don't really get better at gravity, but we do live within the law of gravity. And Conway's law, which was originally stated, um, wow, probably close to 50 years ago, maybe even longer by Mel Conway. Um, Conway's law is extremely important to recognize as we develop software. And if you're not familiar with Conway's law, let me share that with you. Conway's law states that organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. What does that actually mean? It means that when we develop software, very simply, the software will reflect the level of communication that we have and the quality of communication that we have. Some readily say that this means that if we have three teams, that naturally we will have three subsystems. It's that sort of organizational structure that makes that uh, this law prove true. I actually don't find that necessarily. Actually, if you have three teams, all three teams are working in the same code base and they're all making interchange, uh, cross-team changes that are confusing to each team. And so anyway, I think actually what this law um, may be more clearly seen as having an overarching um, influence on is the communication within a single team. How well does that single team understand the business requirements? And if you take that funnel strategic failure that I showed before, this is the kind of communication structure that I think is more damaging to the end software development and the one that can be most readily changed. So remember this structure? What does that actually amount to? It can amount to this, where software developers basically have a gag order. They are unable to say anything about the software. They just implement it, right? Just get it done. The executive message is just to get it done. And then there's this situation, the business expert. Who is the business expert? Do we know even who they are? And if we know who they are we able to talk to them? Are we permitted to talk to them? Or is that not permitted within our organization? So Conway's law, it's our choice. If we change our communication structures, right, the structure within the organization of communication, we will stand a much better chance at succeeding. Well, do we then say, haha, we've created this communication structure, achievement unlocked? Is that true? Well, let me talk about the second thing that we must get right in order to succeed with software development or else fail. The second step, Conway's law. Now, this is not a mistake, but the reason that I'm reiterating Conway's law is that once we get the structure correct, we probably still have enormous changes to make in the kinds of communication that we have on a single team. So don't think that just by creating the proper structure that we will work better within the influences of or the properties of Conway's law. So what actually we're looking back at again is this business complexity. And unless we go searching for what we don't know that we don't know, we will never know it and we will continue to deliver ordinary software, even with the best communication structures. So we have to use a learning tool. And domain-driven design is one of the best learning tools because it features communication by a ubiquitous language being modeled within a bounded context. This reflects directly the communication quality within a team that hopefully includes a close relationship with a business person that understands the software that needs to be delivered. But even that business person will not understand entirely what the strategic and tactical steps should be to deliver that software. It will require close contact and continuous communication, not necessarily all day long, but at least at certain parts of the week, and certainly during short time frames within a day, we can accomplish a lot with that kind of communication if we know what our questions are and if we have strong communication. Another thing that's very uh, important in this situation is experimentation. So if we think we have the right answer, write it in code, implement it in code, and see how it feels. Oftentimes, when you're just drawing on a whiteboard or doing event storming, you will think that you have the answer, but as soon as you start implementing code, you will find the holes in your uh, in your learning, and you will have to go back because the code will reveal that you haven't learned enough. Or by implementing the code, it will show problems that you need to ask more questions about, and those questions will lead to breakthroughs. So it's all about communication and codifying the communication into a domain model that is constantly being improved. I like to say that learning results in knowledge and knowledge changes everything. It really does at any level in life. And, and a large part of our life is spent developing software. Learning will change everything about the quality of the software that we deliver. And domain-driven design is one of the better ways to do that, both strategically and tactically. We can make such advances. So the real achievement that we're trying to unlock is team learning. We're building a structure that enables strong communication, but we actually have to use strong communication within that team structure in order to actually achieve good results, the superior results. Now, if you think that I'm going to say that the third thing that you have to get right is Conway's law, I'm not going to say that this time. So surprise. I'm going to say what I've alluded to and maybe even hinted toward throughout this discussion or presentation is that modularization is extremely important. The modules that we use should reflect the communication structures that we have. And so throughout the software, we will tend to have conversations with different business people, different business experts, and the modules of our software should show those structural differences, those communication differences. So again, here's where we are. Here's where we are. It makes money, but it's not a good thing. So to transform that, modularization is extremely important. And note again that all 7 of these medium-sized modules or even small modules are extremely important because they encapsulate the conversations, 7 different kinds of conversations that we have in the business. So these actually reflect the communication structure, not just the team structure. And because we're modularizing the communication structure, which could even be the same software development team on any number of these, we're still having, as a software development team, different conversations with different business people in order to make this system work. Another thing that's important to note here is that each of those 7 modules can also represent 7 different architectures. The architecture is not necessarily of necessity driven by that outer container, which is the monolith deployment unit itself. So we can actually create the correct architecture within the individual modules. And this would also include separate databases, or at least clearly separated tables with separate permissions within a single database that can then be easily translated into a separate databases when we go into a microservices implementation. So now those 7 modules that we had before could be broken out of that monolith and implemented as microservices. So this is the kind of transformation that we're talking about. Yes, we're making money, but look at the nice, neat piles of money that we have. This is where we have are reflecting a strong communication, not only in structure, but in the actual quality of the discussions that we have as teams. I'm going to end now. I had a few more things that I wanted to say, but my time has, I've gone over time a bit. I apologize, but let me end here and have some communication with your side. Hey, Benjamin, I guess nobody minded my overtime.
I think they were pretty interested.
Okay.
They were pretty interested, I would say. So the idea is maybe now have first a short break, right? What do you think? 5 minutes, 10 minutes?
That's fine. Whatever you, which would you like?
5, 10, 5
Okay.
minutes,
Okay.
and then we go on, so everybody can grab a drink and do his business stuff.
We'll start at 1600, right?
Okay. Yeah. Awesome.
Yep.
See you.
See you in a few.
Eine Frage. Ich habe eine kleine Hilfstasche gesehen, als ich gesehen habe, dass er nicht geht. Hat er irgendwie schon gesehen. They come back. So I think they just wanted to have the 5-minute break to get faster to the beer. So in the meantime, Marco Emmerich has left. So because he wants to travel back to Nuremberg to his family. So we will have to see how many people will join for the Q&A. Maybe we'll do it more casually. I will just have a look how much time we have to the Q&A, because I think you could also talk about your workshop, by the way, in Hamburg, if you want to. Just briefly, maybe now, before the session. Show this one. I don't know. Might be interesting for some. So panel is 1640. Yeah, perfect match, I would say. Not much break towards the panel then. Eberhard Wolf said he wants to join the panel, but besides that, I'm not sure if Marco will join. I will try to reach him during your talk. Yeah. So you need to unmute your microphone, by the way. Ta-da, still red.
Okay.
Going, awesome. Okay. So we start with the next session, I would say. Any questions from your side so far, currently?
No, I'll try to use a stopwatch this time.
Yeah, no worries. I think we are quite kind of flexible. So everything is good. Just proceed as you are comfortable. I can write with Eberhard PMs on Twitter, so it's no big deal if we postpone 5 minutes or 10.
Okay.
See you. Have fun.
Okay. All right, so we're going to switch topics now. And I mentioned earlier discussing reactive DDD. So this discussion is about
full screen for the presentation.
Oh, it's not full. Okay, sorry. Let's see.
The other full screen.
Is this correct?
Yeah, perfect. Looks perfect. Yeah, awesome.
Okay, so reactive DDD with message streaming. So this topic is, quite involved. What I'll first do is introduce you to what reactive means, and well, we've just discussed DDD, so I won't have to spend too much time explaining DDD, but there will be some explanation. And then finally, what is message streaming? Okay, and then I will give you some implementation details about message streaming, how this works, and we'll be looking specifically at the reactive streams specification. So this is a presentation that, while not based entirely on the Vlingo platform, certainly does include Vlingo as a kind of reactive platform. This information can be used with other reactive tools, though. So the main portion of my presentation doesn't necessarily have anything to do with Vlingo. So what is reactive? Well, underlying all of the reactive attributes or characteristics is message driven. So whenever we're talking about reactive, you pretty much have to think in terms of message driven. And while reactive doesn't necessarily say that message driven must absolutely be parallel, certainly it has to fill the requirements of at least asynchronous. And that's because we have to support the other characteristics of reactive, which includes responsive, resilient, and elastic. So by blocking, long-term blocking, even when I say long-term blocking, I may mean as little as just a few milliseconds, but still this kind of blocking can cause an overall stall in the entire service, let's say a microservice, or even in the entire system. So we achieve responsiveness by making message delivery asynchronous. And with the style or the hardware architectures that we have today, it is not complex even to enable software developers to use asynchronous, concurrent, even parallel processing. And so our software can be quite responsive. To give you an idea, on the Vlingo platform through our asynchronous HTTP server, the Vlingo HTTP server, we often experience sub 10 millisecond request response round trip. Okay, round trip. So I've seen as low as 8 milliseconds for a full round trip request response. So quite performant. This responsiveness then leads to elasticity, and the message driven leads to elasticity because it means that the number of nodes, let's say, or the scalability of the service that we're working in, so inside the service itself, is actually elastic. It can expand and contract as necessary depending on the load. So it means that we can scale the architecture itself because of the message-driven nature, and the elasticity enables the entire service to remain responsive after there is a lot of load. And then when we scale back down, the responsiveness will still be relative to the load that we see at any given time. It's also resilient because of message-driven. The very nature of the way that message-driven is implemented sort of lends itself very well to resiliency. That is because when you send a message asynchronously and an exception occurs inside the component that is receiving the asynchronous message, there is no call stack back to the sender of that message. And so in order to handle any sort of failure in the receiving component, you have to deal with that in a different way. So it means that we don't just, throw an exception back to the client, the one who sent the message. That's actually not really, well, it is possible, but it's not a thrown exception. It is a delivered exception. So the point is, if a component that is receiving a message throws an exception, it must have a supervisor in order to deal with that. And the supervisor kind of architecture with this message delivering architecture means that the system tends to be naturally resilient because a supervisor is designed to deal with failure and the kinds of failures that each kind of component can have. And therefore, it will know what to do about a specific kind of failure. That could be stop that component. It could be tell that component to continue, but to ignore messages of that type and log them, or pass those messages on to some other recipient to deal with the the error condition, and so forth. So when I was quite a young software developer, I think I had been developing software for about 2 years. I got the opportunity to meet Admiral Grace Hopper, one of the more notable personalities in software development, and um, incredibly gifted and uh, well-spoken, and actually outspoken. She was quite forceful in her delivery of the importance of certain, you know, adhering to certain, uh, um, let's say, you know, maybe sticking to our determination to write software in a very efficient way. And in order to emphasize that, I was in the audience when she was giving a talk. This took place in Denver, Colorado, in the U.S. And she handed out um, this wire to everyone in the audience. Got a wire, and this is a wire that you would think of as being like associated with an old telephone line or whatever. It could be a you know, a network cable or something, but where you break open the network cable and you take just one of the little wires out of that are kind of wrapped up. I think you know what I'm talking about. They're usually multicolor. Each wire has maybe a yellow and red or something like that, stripes on it. And she hands out this wire, which I think is probably, I'm going to say it's maybe 5 centimeters. I'm not very good at metric, but I would say it was maybe 10 inches long. And she said that, let's say in that 5 centimeters, that this was the length that light could pass through a wire in a nanosecond. And Admiral Grace Hopper said, "We are wasting too many nanoseconds." Even this was probably back in 1986. Okay. She was saying we're wasting too many nanoseconds. Don't waste nanoseconds. And so everybody who attended her talk had to take home that nanosecond in their hand, a physical representation of a nanosecond. And I'm telling you, that stuck with me. But it wasn't just her talk that motivated me to have this viewpoint, because I had to develop that viewpoint even a few years earlier on my very first programming assignment, because we were dealing with diskettes back then. So this is where the IBM PC was first introduced, well, in 1983. So I'm using that um, IBM PC just a year or two after it was released. And now I'm developing software that works on diskettes. The company that I worked for at the time, my first job in software development, had a COBOL based system using Microsoft Micro COBOL. I forget exactly what it was called, but it was COBOL for the PC. And in order to run that software, it required 10 diskettes, 10 diskettes with chained operations between each diskette. And this was a huge pain for the company because they were sending out insurance-based PCs pre-configured for telecommunications, and the operators of this software would have to change diskettes in and out of what was called the program drive. And there was a second diskette drive for the data. And I had to develop software that replaced those 10 diskettes with a single diskette. So now, instead of telling the user, insert disk number 3, and then press any key, so they would try to find disk 3, take disk 2 out, or whatever the disk was that was in there, insert disk 3, close the door, and hit any key. And there were even speed problems with that, because sometimes the door, just latching the door of the diskette drive, took some time, that once you latched that, the drive would then start spinning. And if they latched it and pressed the key too soon, it would cause failure. There are all kinds of problems around this, even just selecting the correct diskette to change. So my mentality from way long ago, a long time ago, okay, 36 years ago, has been on creating small, tight, fast software. And when I heard Grace Hopper talk about the nanosecond, it just thrilled me. I was like, yes, we're speaking the same language. Okay, so this is my mentality from my first entry into the software industry. And so I just want to say something that Donald Knuth said these words: premature optimization is the root of all evil. He did say those words. But just as with DDD, context is so important with DDD, context is so important when we quote people. And I want to just share with you what Donald Knuth actually said. Donald Knuth actually said, we should forget about small inefficiencies, say about 97% of the time. Premature optimization is the root of all evil. Yet we should not pass up our opportunities in that critical 3%. Now, what I want to say about this is, when Donald Knuth said this, it probably did amount to 3% of inefficiencies that we would have to optimize around. But the inefficiencies in software today are very, very high because the software that is designed today is not made for the hardware architectures that we're running on. Probably far less than 1% of all the software delivered is actually running or designed for the hardware that we have been running for nearly 20 years now. Okay. So an axiom that I think is very important in software these days is that blocking is not a small inefficiency. And we are blocking far more than 3% of the time in our software. Most of the blocking that we experience is maybe thought of as being blocking in, uh, in accessing a database. And that is a large inefficiency because we're blocking threads on disk access and network round trip. But that's not the only blocking that we're doing. All of the software that we write that makes method invocations, direct method invocations on objects, blocks. So we are blocking all of the time in software development. So this is an axiom that I think is quite important to realize today. And I think that if Donald Knuth were to comment on inefficiencies today, he would have to say that most software is highly inefficient. And let me just skip here to Donald Knuth also said, people who are more than casually interested in computers should have at least some idea of what the underlying hardware is like. Otherwise, the programs they write will be pretty weird. Okay. And that's a funny statement. I mean, to me, that's like funny, but it's also very true. And today, we do not, as an entire industry, have any idea whatsoever of the underlying hardware that we are using. We depend on the software that we use, perhaps the programming languages or libraries or frameworks, to be more efficient. We, as application developers, and I have to say, really, even tool developers, we are not well educated in the underlying hardware. And so the programs that the industry is creating are highly weird. And this is because from way back in the 1960s, when Moore's law became known, that processors would tend to double in speed every 24 months. That was not only true, it was actually false in the sense that we tended to see those kinds of exponential increases in power about every 18 months. That all continued. And so the software industry became very used to, hey, you know, this piece of software that I'm running, this program that I'm running is slow. Well, I'm just going to buy a new computer with a faster processor. And that kind of mentality continued until about the year 2003. And what people actually didn't realize, even at 2003, that clock speeds just stopped increasing. And there was a lot of ignorance around this because people were somehow blaming the chip manufacturers for this decrease in speed. But it is actually a physics problem, in that if you can't cool the processor and if you can't solve other problems physically with the processor, you cannot increase the speed. And this is what Intel and other um, chip manufacturers and chip designers now understood. And so CPUs were not getting any faster. So what did they do? They first introduced the hyperthread. This is where you had a single CPU or a single core, but that could run two threads simultaneously through the processor. This was followed by multi-core. And multi-core also had hyperthreading. So basically, if you have 4 cores in your machine, you can run 8 threads simultaneously. So count the number of cores, multiply by 2. This is the new hardware architecture that is actually not new at all. It's almost 20 years old, and we have been ignoring it largely throughout the software industry. So the axiom premature optimization is the root of all evil. Well, let's just say that when we're talking about chip efficiency, I have to reject that statement. And while I can certainly not speak for Donald Knuth, I think that this message would change today, because it has to be recognized that the software in our industry is not written for the optimizations that are automatically provided by the processors that we use. And so what are we used to? Objects that block. So a client object in the same virtual machine, as in the same process, the same Java process or the same .NET process, a client object makes a method invocation on a server object. That method invocation blocks. There are no two ways about it. Oh, so we have threads. Yeah, the natural tendency for all of software developers is to say, well, I'm just going to use threads then. Let me go back home and I'll start implementing this really awesome multi-threaded program. Well, threading isn't as easy as we might think. There are all kinds of situations where blocking can be introduced even accidentally. And if blocking isn't introduced in some way, most software will fail under a multi-threading situation. If you want to understand why, just go to the Wikipedia article on the Java memory model and see why two threads that are trying to access the two data, the same data, will frequently not see the same data at the same time. So this is where I want to zero in on the other two smaller aspects, the small print or the fine print of reactive. Reactive is also maintainable and extensible. So if you're trying to create your own homegrown multi-threading, just be aware that it's going to be very hard to succeed with that. You will tend to not create maintainable software, and that software will tend to not be extensible. One of the best ways to use multi-threading is to leave the multi-threading to the system itself and accept the fact that individual objects will look and act single-threaded. This is by using the actor model. Alan Kay, the person who coined the term object-oriented and who delivered one of the first entire programming systems called Smalltalk that was entirely object-oriented, said that the big idea is messaging. So object-oriented's big idea was messaging. And Alan Kay says that the actor model basically represents objects done right, or objects the way that he intended them to be used, where the big deal is the objects themselves from the outside and the messages that they exchange between each other. So Dr. Carl Hewitt, just about a year after Alan Kay delivered the first implementation of Smalltalk, discovered the actor model. And Carl Hewitt then, released this information to the world, but unfortunately at the time, the hardware architecture and the networks that we had would not really, didn't have the capacity for dealing with this kind of software design. That is because in Carl Hewitt's day, clock speeds were well under 1,000 megahertz, probably right around 800 megahertz or so. And transistors, there were a few more transistors, but we had a long time before we saw the kinds of situations where the actor model could actually be used successfully. Later on, in about the year 1996, so roughly 13 years after Carl Hewitt published information about the actor model, Joe Armstrong and his team created the Erlang programming language, which effectively used the actor model. But in my understanding, Joe Armstrong and his team were not aware of Carl Hewitt's work. So they sort of rediscovered, and this goes along with sort of a saying that I've heard, that there are usually two discoveries in software: one in academia, which is where Carl Hewitt was, and one in industry, which is where Joe Armstrong was working. So again, DDD is about communication, learning, language, and context. Conway's law, again, is about the communication structures, but also how we use communication even when we have strong communication structures. Similar, message as before. I'm going to roll through this. And with multiple languages in DDD, because each of these separate microservices or even modules within a monolith are talking to one another through messaging, or can talk through messaging. And this is where multiple domain languages, as in bounded contexts, must map between each other in relationships, as in the language spoken in the model, in the software model in the upper left, is different than the language spoken in the software model at the lower right. And so if those two need to exchange information, there has to be a mapping between those two bounded contexts. So messaging is, of course, message passing, but message passing with intentions. So the intention of do this is communicated in software through a command message. And the communication of this is a fact that this happened is communicated in software through a domain event. And so these kinds of messages can flow between multiple bounded contexts, but they must be explicit to be well designed. They must be explicit in their intention or in their relaying a fact about something that has previously happened. Okay, so now let's talk about streaming. What is streaming? Streaming is handling streams of data, especially live data, and we don't often know the volume. It's not predetermined. And so we turn on sort of a hose, and when we turn on that hose, the water may just keep flowing and flowing, right? The reservoir will not run out of water before we decide to turn off the hose. So this requires special care, and asynchrony is extremely important in the case of message streaming. Blocking does not work out well with message streaming. So the challenge is, though, what if our source is like this fire hydrant? We take the block off of the fire hydrant, and the stream is more than a stream, it's a blast of water. What can we do about that? Because what can happen is from the source to the sink can continue to fill. And if it continues to fill because the water is flowing more quickly than the sink can process it, then it becomes overwhelmed. And this is the situation that we have. So the reactive stream specification specifies a few different concepts that are not entirely new to any of us, but the implementation of those concepts is very, very important and outlined in the reactive stream specification. The first concept is a publisher. So a publisher obviously publishes a stream of data elements of some kind. The stream of elements can be seen by a subscriber. So the subscriber subscribes to the publisher, and the subscriber obtains a subscription from the publisher, and the subscription is the subscriber's means to communicate live with the publisher. And there's also a processor, and a processor is basically, let's think of it as a publisher, as a subscriber on one side and a publisher on the other. So the processor would be subscribed to a publisher, but what it takes from the publisher as data elements will then be transformed internally into some other kind of data element, and it will be pushed to its subscriber or subscribers as a different kind of data. So this is a sort of functional transformation that says A to B. So A is the incoming stream and B is the outgoing stream. Or if you're a Java developer, it's usually referred to as T to R, right? So type to return type, but essentially the return type becomes the flow. So maybe A to B works better in this case. Well, this is why asynchrony is extremely important with reactive streams. There's a contract between the publisher and the subscriber that says, I, the subscriber, will tell you, the publisher, how many messages that I can receive or how many data elements I can receive at any given time. And so the subscriber will tell the publisher, I request that I receive this many data elements at a given time. This might be 5. It may be at the highest end of a signed long integer, which could, relatively speaking, take 33,000 years to reach that full value of a signed long integer. if you were to receive even one message per second. So basically, a subscriber can say, I'm going to open the pipe, send me as many data elements as possible, or I'm going to narrow the pipe and I'm going to say, I request 5, 10, 100, 1,000, whatever data elements at a time. Then the publisher has a contract with the source, and it says, I want to pull this many elements from you, and the publisher will then receive some number of elements from the source, and then the publisher will push up to n elements to each subscriber, and each subscriber has their own request limit. This creates what is called back pressure. It means that the sink cannot easily overflow unless the subscriber does not understand what kind of flow that the sink can tolerate. But normally we want to build the intelligence into the subscriber that says, I know my sinks and my sinks can only handle this many elements at a time. But you see the importance of this back pressure to not cause the sink to overflow. Back pressure is also seen in a processor. So notice this side, the left-hand side of the processor in the middle, is a subscriber. It is telling a publisher, just like the other subscriber in the previous slide said, this is my back pressure or this is the number of elements that I can receive at any one time. And the publisher pulls the source for some number that will not overfill or exceed the number of requested elements. And then it will push those to the processor, which on this side, on the left-hand side, is a subscriber. The processor will then transform the data into another kind of data, so A to B, and push that data to its subscribers. But since it is acting as a publisher on the right-hand side, it will also adhere to its own back pressure that subscribers are imposing on it. Okay, so this works consistently between different kinds of subscribers and publishers. How do we use reactive streams? Well, in a lot of different ways, a lot of different opportunities to use them. But note that when we're streaming across different bounded contexts, it often means that we have to understand the kinds of data that we are exchanging. For example, let's call this the bounded context that's at the top of this slide as an upstream context. And this makes sense just from a positional standpoint. This context is upstream, which means that the downstream context at the bottom of the slide must understand, for example, at the far left, what are the kinds of commands that I must send to the upstream context to get it to respond to me, to get it to do something in behalf of my context. It also means that in the center, when a domain event occurs in the upstream context, the downstream context must understand, what is this event? What is its name? What is its structure? How should I consume it? What does it mean to me, to our bounded context? Or it could be that the downstream context executes a query on the upstream context, and the downstream context will then consume a document object, let's say, which is the white on the far right, the white message element that's moving to the downstream context. So all of this information exchange has to be well understood between bounded contexts. Architects and developers love streaming. Wow, it's really like developer candy. We love that stuff. But you know who worries about this? The CIO and senior VPs and directors and all kinds of management worries about this. Why? Because Who is dependent on what? I have literally had these conversations with CIOs, senior VPs, and on down the line. Who depends on what? So Julia is a very busy CIO. She's got so many things to deal with. She has meetings with the CEO every morning. She's, trying to deal with a staff of hundreds of individuals, or potentially even thousands of individuals. And she has some big questions about, okay, I hear about all this event driven stuff, but what are the dependencies? When is this all going to crumble? When someone pulls a dependency out from under another service, what's going to happen to our entire systems across our enterprise? This is where DDD published language comes in. This is where published language says, I, as the underwriting, this is in an insurance setting, I, as an underwriting context, have a published language, and that includes the policy issued domain event. So when a policy issues, or when a policy is issued in the domain model, the domain event policy issued will be created, and that domain event can flow to downstream bounded contexts, and it can have an impact. Like you see in both the claims and the inspections context, we actually create a corresponding policy, but it is not the same policy because, again, remember, the conversations that we have in the upstream context are different than the conversations that we have in the two downstream contexts. And so a policy in each of those contexts will mean something different than it means upstream. What does that lead to? It leads to that either one of those subscribing bounded contexts downstream will likely not receive all of the information that they need to perform some operation aspect of the published language of the underwriting context. They can make, for example, a REST query using a GET and query back on the underwriting context and ask for an issued policy data document for a single operation. So this downstream subscribing context will not cache that policy data, the issued policy data. It will only cache very little information, that possibly not even all the information that was conveyed through the policy issued domain event. And when it needs more data, it will go get it just in time. And it will throw away that data after the single operation. It must not cache it because it is not the owner, it is not the authority of that data. And caching it downstream could actually, in some cases, lead to catastrophe, or at least very big problems in a financial or healthcare or other kinds of critical environments, or just being plain wrong about the data that we're making decisions on in the downstream context. How do we exchange that data? We use a published language. The published language of a bounded context is saying, this is the language that I am willing to talk to the outside world, have conversations with the outside world. And so an upstream context will require downstream contexts to speak its published language, as in a downstream context can send these blue command messages, and it can receive these orange domain event messages, and it can receive these document query results or query results of document type messages, the white ones on the right hand side, and other kinds of messages. But notice that the definitions of these messages are housed in a schema registry. This is extremely important because this is going to solve problems not only for multiple teams who are consuming and exchanging information with messaging, with reactive messaging, but it's also going to solve the problems for Julia, the CIO. That's because every schema within a registry is broken down from organization to business unit to context within that business unit, or you could say microservice being a context. And this is a namespace that says this published language of commands, data, documents, envelopes, events, and so forth all belong to this context. And if you want to make a dependency on that, you have to give your credentials as the service who is forming a dependency on it. Therefore, we know who depends on this published language of this particular context. Again, this is what helps Julia to sleep at night, knowing that where the dependencies are, and if something goes wrong, who depends on what version of a given schema. So within a commands category, we have individual schemas of individual commands and different schema versions within that schema. And we have that same kind of information hierarchy within each of the categories within a context. Therefore, notice that, for example, as we support with the Vlingo schemata schema registry, a namespace might be done by me, peer-to-peer economy or P2P matching. So matching is the context. And within our events, within matching, this is the published language of the events that we publish. Proposal submitted, proposal resubmitted, proposal pricing rejected, and so forth. Then notice that we use a semantic version within our schema registry. Each schema has versions according to a semantic version. Any two versions that share the same major version must be compatible with each other. Or in other words, at the top, proposal submitted, 1.1.0 must be backward compatible with 1.0.0. However, because the next version of 2.0.0 does not share the same major version, we are permitted to make a breaking change in 2.0.0 of proposal submitted. Also notice at the bottom of this that there are a couple of different states or stages that a schema can be in. It can be published, as in proposal schedule verified is published at 1.1.0, but let's say that we create a new version, such as 2.0.0 of proposal scheduling verified. We can put that initially into draft mode. This allows different bounded context to use this draft mode or draft status domain event, but with the understanding that this domain event may change over iterations in development, and it will not be fixed as a fixed type unless it is published. And so once we go to published, that domain event is golden at that version. It must not change from that point forward. And this gives the opportunity for development teams to work in iterations and improve schemas over time, but still allow separate teams to consume the new domain events and so forth in an experimental or a pre-production manner so that they can make the adjustments as necessary. Vlingo schemata also provides command line tools, so you can go fetch a schema that you rely on, and you can go also push your schema version up to the schema registry and so forth. And this is currently provided through a Maven plugin. So let me show you just a few examples of streaming. And this example is where we have a map. So we have operators in Vlingo schemata, and this is a mapper operator. And the mapper operator says that I will map a string to an integer. So this is the A to B mapping that a processor might use. And so when the processor receives as a subscriber a string, it can turn that string into an integer based on this mapper. And then when we run that mapper, by performing it at the bottom, we can take some number of digits that are provided through this list, this string list of 1, 2, 3, separate string 4, 5, 6, separate string 7, 8, 9, and we can transform those into numbers and put them into the result array list or list of integers. We have similarly operators that are filters. And by the way, the mapping filter can do flat maps and so forth. So not limited in the kinds of mapping that can be done. So as you can imagine, we say at the top that our operator will filter and say that any string that contains the digit 1, the character digit 1 in it, will be filtered in, and all other strings will be filtered out. And therefore, the result of that's in this list will eventually be the strings 321, 123, and 214. All the other strings will be eliminated. Okay, so notice here an example of the full operation now of a reactive stream. This is where we have a journal, and a journal can hold any kind of source, such as a domain event source or a command source. So we can put any kind of source into this journal. And so we would think of this journal as being an event store or an event journal, domain event journal. So we can ask the journal to stream all of the events that are in the entire journal from the beginning. And as we receive that stream, you see that we have the and then. So and then, because the stream all of, that is an asynchronous operation. That asynchronous operation will complete sometime in the future. The dot and then says that when that completion is available, I want the stream that is the outcome of that eventually completed operation. And I'm going to take that stream and I'm going to flow into a consumer sink. And that consumer sink is going to do some analytics. It's going to take all events that are related to proposals in the matching bounded context, and it is going to perform an analysis on each of those events. And then it's going to relay the performance results at the very bottom to the next in our pipeline. So this is perhaps working within a publisher, a processor, and the next operation that will be performed will be done with this perf. So, and then notice finally there's a 10 at the bottom here. This means that the stream will flow in to this consumer at the rate of a maximum of 10 elements at a time. So this is the back pressure value that says give me only this many domain events at a time. So that's what I had for this. I've gone overtime again. Well, congratulations. I've gone 6 minutes overtime, and I apologize again, but I will say it's pretty difficult to speak when I can't look at the people that I'm talking to because I only see my screen. But again, we're going to transform this. If this is sort of one of the main ways that we're going to be delivering conferences and other events in the future, we're going to have to improve this. And I'm sure that there's several already working on this. So let's look forward to that digital transformation. But thank you, Benjamin.